All right. Thank you for coming to my talk, and sorry about the technical difficulties here. I'm going to be talking about Linux kernel exploitation for beginners. The purpose of this talk is really to try to lower the bar of entry of getting into Linux kernel exploitation. When I first started to get into it, I thought it was completely unapproachable, but it's not. It's actually pretty easy and a lot of fun. So what is Linux? So Linux Linux is a kernel. It's an operating system kernel, and the kernel is a core component of the operating system. It's responsible for managing resources such as processes, memory, storage. It handles all the interactions between software and hardware. So any of the programs that you're writing, if you're running printf, that has to go through the kernel to ultimately print that text to a screen. It also provides security and isolation. So you've got things like permission management, memory isolation, and process isolation. Why? Why would we look into exploiting the Linux kernel? Well, the kernel runs in a privileged context. It has a very large attack surface. There's kernel modules, there's drivers, there's syscalls, there's all sorts of subsystems. You can entirely focus all your efforts into a single subsystem, or you can look at all of these different parts and pieces of the kernel. I think it really helps people develop practical understanding of OS internals. So what's actually going on under the hood? How do things like free lists and memory managers and process management, how does that all work? You get really good insight into that by trying to exploit it. And Linux is widely used, even in presentations, even though it doesn't work. But yeah, you see it on tons of servers, you see it in embedded devices, you see it in appliances, vendor appliances, phones. Android obviously is super popular. All right, and specifically, I want to focus on kernel CTFs. So why CTFs? Well, there's going to be reduced complexity. So you're going to have limited background processes running on your OS. You're going to have a more predictable memory state. It's going to be a lot easier. You don't have to deal with the things that you would see on like a production system or an embedded device that's actually doing things other than handling your exploit. There are certain barriers to entry are also lowered when you're doing CTFs. So you're going to get a precompiled kernel image. You're going to get a pre-compressed file system. You're going to get some actual source code for the vulnerability that you're looking at. Makes things a lot easier. Also, from what I've seen doing a bunch of kernel CTFs is a lot of times the focus of the CTF isn't exactly on the vulnerability. They tend to be a little bit easier and simpler to find and to exploit, but it's really on the exploitation strategy. It's after you've found that vulnerability, after you've developed a proof of concept, how can you actually achieve a root shell or elevate your permissions or whatever it is. What I really like is that these challenges are customizable. So unfortunately, I won't be able to do the demo that I was planning on doing because I don't have my laptop. But I actually did customize an existing CTF challenge for that demo. And all the screenshots and whatnot come directly from that challenge. So we'll see that as this process goes on. All right, so what does a challenge look like? What is the structure? So typically, you're going to get a handful of files, in a gzipped directory, and what these usually contain is a compressed kernel image. So that's our BZ image file right there. We are going to get a compressed file system. That's that initramfs2.cpio. And the CPIO extension is important here. So within the kernel itself, there's actually a mechanism for decompressing CPIO files. The initramfs is like It's an in-memory file system that's actually used to kind of bootstrap the system. So if there's any kernel modules that need to run, or if there's any other setup that needs to be done, it typically happens from that directory, and then the actual root directory gets mounted for a production system or a laptop. You're also going to get a source directory typically. This isn't always the case. Sometimes they'll only give you, like a pre-compiled kernel module that you have to reverse engineer, but we don't need to focus on that now. That's a little bit more challenging. But for the most case, you will get some source code with the actual vulnerability contained in it. And then you're going to have your actual run command. So that startchemu.sh is a bash script. And we'll take a closer look at the one that I used for this presentation later. But that essentially just starts the challenge. So it runs this compressed kernel image, it attaches the file system to it, and off to the races. All right, so how do we do some initial recon on here? So you'll see on my right-hand side, your left-hand side of the screen, there is a small little bash script here. All this does is it removes that initram fs file system, it recreates it, and then what it does is it actually decompresses the CPIO compressed file system. So what this is decompress that file system so you could take a look at what's inside it. Up here, you can see that I've listed this directory and I've specifically highlighted the init file. Very often, the challenge setup details will be contained in that init file. And I'll go into a little bit more about how initram fs actually works with that init file. But what you might also notice is we don't have a home directory here, but we do have a root directory. So if we take a look at our root directory, we can see, yep, there's some challenge files there. There's a README file, usually offers some hints and where to look around. And then there's also that .ko file. So .ko file is it's a compiled kernel object. It is what our kernel module is. It's what gets loaded into the kernel, and it's what we'll be interacting with during this challenge. All right, so like I said, initram fs is that in-memory file system. It uses that /init file as the first user space script that gets executed after the initram fs file system is mounted. So like I said, a lot of times the setup process and any challenge-specific stuff can be found in that init file. I've got the init file details here on the left side of the screen. And although I said that typically the setup process happens within this file, it actually doesn't happen here in this case. So we've got to go look around for some more files. If you're familiar with Linux startup processes at all, you probably know about the init.d directory. So we've got this S99 CTF file in there, which is quite suspiciously named. So if we take a look at that, we can see our actual challenge setup details. So I'll just walk through a few of the highlighted sections here. So I'll start with the first yellow section. So what we could see here is that .ko file, that kernel object I called out before, is actually getting loaded as a module. That's what that nsmod command does. So it's loading that as a module, and then it's actually creating the character device after. So that character device will be something that we're interacting with as part of this process. That'll give us access to that kernel module. And then you could see the set SID command below. That's actually specifically setting what user we will be. And when we go through how to debug these challenges and how to actually develop an exploit and stuff, we might modify some of these things. But going back up to the top of this file, we've also got some other highlighted sections. Well, these aren't necessarily challenge specific. Sorry. Well, while they're not necessarily challenge specific, they are, I'd call them hints. There are a few different hints to how we can exploit the system and what targets we can look at and whatnot. We'll get into the details of them later, but just know that those are some hints that we can use to further our understanding of how this challenge works. All right, so typically we've got source code, so that's going to be one of the first things that we look at. This is a fairly simple, vulnerable kernel module. There are some kernel-specific functions that I'm going to talk about, and then I'll just kind of talk through each of these functions, what they do, and what functionality that provides for us to use. So as you can see, we've got a new, a delete, an edit, and a show command. The new command is making use of a kernel-specific function, that kzalloc function. If you're familiar with malloc or other memory allocation functions, it's very similar. It is a heap-level allocator that lives in the kernel. It will give you objects of certain sizes that fit into certain caches. Also, going down next, we've got a delete command. It's got essentially the antithesis function, which is k-free. Same thing, it's for freeing that memory that you've allocated, and this is all kernel specific. So these commands these functions will only work from kernel context, from kernel space. They do not work in user space. And then following that, we've got this edit and this show command. And if you look at these, they look very similar. And they're essentially doing the opposite things of each other. So the edit command calls this copy from user command to copy data from user space into kernel space. Very similar to like a mem copy if you're familiar with C. And then in the show function, we can see the copy to user, so it's the reverse. So we're copying from kernel space into the user space. These are the standard functions for copying data back and forth between user space and kernel space. So you see them a ton of times in these challenges. But yeah, if you're familiar with memcopy or any of the copy functions, they function very similarly. One thing I do want to call out too is that we've got these controllable allocations and deallocations. And what I mean by that is we are passing a size that is user controlled to the kzalloc function. And the way kernel, the way like the kernel heap allocation works is depending on the size that you're allocating, it actually will fit it into a cache, a general purpose cache, which are, they could be like 32 bytes long, they could be 64 bytes long, and so on. It goes up from there. There's, as kind of an aside, there are also object-specific caches. So there's certain objects in the kernel, let's say a structure to define a TTY struct is something we'll talk about later, which is like a pseudo-terminal struct. They actually have, in newer kernel versions, a specific object cache which caches those objects. So that kind of gives you some security, and you'll see why later, but just wanted to call that out. All right. Excuse me for 1 second. Okay. All right, so let's dive a little bit deeper and just take a look at the specific vulnerabilities that exist in here. So as I called out earlier, the size variables that we're passing to these functions are user controlled. And as you can see in this really simple, in both of these really simple functions, is there's actually no checks for that size. So if you've allocated a buffer that's 32 bytes and then you want to read from it, well, there's no check to say, well, you can only read 32 bytes, so you can read as many bytes as you want. And what do we get when we do that? Same thing with writing. So what this gives us is essentially an out-of-bound heap read and write primitive. So we've got the ability to allocate objects on the heap and then read past them or write past them. We've also, as I discussed before, have that flexible heap cache placement. So that's going to really help when we get to selecting a target that we want to exploit. Being able to place your objects in any of these heap caches, it just gives you a ton of flexibility. All right, and talk about some kernel module interaction. So this might not be familiar if you've never written a kernel module before, but there are a lot of specific functions and structures that are used in these kernel modules. Things like the file operation. So anything highlighted in the green boxes are going to be module-specific functions or structures. So we've got things like that module init and module exit at the end of the code that will initialize your module or initialize a function for your module and initialize an exit function for your module as well too. And then we've got that file operations up there. That is where we define the different operations that you can actually do against this kernel module. We've only got one here, which is that module underscore ioctl, and the actual logic for the ioctl module is up above. And what you can see is pretty simple. It accepts some data from user space, as you can see from the copy from user function, and then it runs a switch statement against it, and it determines, okay, are you asking for that new command, or yeah, the new command, the edit command, the show command, or the delete command, and then it runs the associated function with it. And those associated functions are the functions that we looked at on the last slide. We can also see the module initialization function here, module initialize. It does some setup here. What it's doing is registering that character device that we talked about before. So again, this is going to be like a file that you open and interact with. And we'll talk specifically about ioctls just briefly. So an ioctl is kind of like a standard function that's used to communicate between a module or, let's say, any kernel code really and user space. So again, you need some kind of file handle that you could grab onto, but then you can initiate these ioctls against that file handle in order to make use of the functionality that's exposed here. All right, so now that we kind of understand what our vulnerability is and some of the more details about how to interact with it, we can create a proof of concept. So our proof of concept is here. This is the full code minus the includes, but this is it. It's real simple. So what we do here is we open a handle to /dev/buffer. So that is that character device that I spoke about. You can see that in the top there, where open /dev/buffer, read write permissions. And then what we're going to do is we're going to allocate one buffer. So I make an ioctl call to this open file handle, and I pass that new command with it. You could see right above the ioctl call, I actually set some of the criteria that I'm passing through here. So we're going to set an index of 1. That's, it's just based off of what it accepts on its end. One of the things I missed talking about when I was showing the kernel modules earlier was we're limited in the amount of objects that we can allocate, and it's limited by that index. I believe it's 16 or something in this specific case, but it doesn't necessarily matter. So after that, what we do is we set the data field that we're going to eventually pass to just a string of characters that's easily recognizable, a bunch of A's and a bunch of B's, capitalized, real easy to see in memory. And we're going to initiate another ioctl, and that ioctl is an edit one. So this is actually going to do that right now. So it's writing those A's and B's to the buffer object that we've allocated, and yeah, that's done. The next thing we do is we actually set the index to 2 because we're going to do another buffer allocation here. So again, we make an ioctl call to allocate another buffer, and then we make another ioctl call to do the edit and write those C's and D's. Again, these are just identifiable strings that we can see in memory later. Excuse me. All right, after that, we're going to do what I've labeled as leak request. So essentially what we're doing here is we're going to do another ioctl on that first index. So you can see I set the index to 1, which should be associated with our first object that we allocated, but I set the size to hex 800. So if we see earlier, we had each of these sizes set to hex 3E8, which is close enough to hex 400, which is really the target size that we're looking for, the target size of the cache that we're looking for. So essentially, I'm doubling that. So the idea here is if I do a show with that hex 800, and I should be able to read all of object 1 and then all of object 2, since they are allocated adjacently in memory. So once I do that, I just do this little for loop here and print out what I've leaked in 8-byte increments, essentially, and in hex values, because it's easier to see pointers and stuff like that when you're printing the hex, and we be able to see our actual values here and confirm the leak. All right, so talk a little bit about the debugging workflow. So before getting into actually running this proof of concept, we need to do a little setup on our challenge here. So what we could see at the top, actually let me take a step back. So what you can see here is that start QEMU script. So this is the script that runs our challenge, essentially. So at the top there, what I've added, or what I should say is all of the yellow bits are actually added to this. So they were not included in the challenge file. All they do is expose different capabilities that I'll be using to debug this challenge. So first one we've got is this section. It does the opposite of that decompress script that we saw before, and it just recompresses our initramfs file directory before we use it. So this makes working with the challenge really easy. You can update files in there. You could put your exploit into that file system. Update any of the files in the file system, and then when you run this, it'll just recompress them. So just makes life easier. I've also added to the QEMU CLI commands this -s. So that -s just essentially exposes remote debugging. So you'll be able to connect GDB or a similar type of debugger based on adding that. Another change I made too was I disabled KSLR. KSLR is the kernel version of ASLR, which is address space layout randomization. Essentially it just randomizes the base address for a lot of different components. One of them being the kernel code, which we'll look at later. Something else that I did was I adjusted in that init.d script that we looked at earlier, the challenge setup. I adjusted that to not give us this random low privilege user and actually put us in as root. Again, this is all debugging purposes. These are things that we'll remove when we run our actual proof of concept and when we run our actual exploit, but they're pretty much necessary to do the work that you need to. What you can see down here too, so earlier when I called out in the initialization scripts, there were some hints there. One of them was this echo2 to proc sys kernel k-pointer restrict. So what that does is it essentially zeroes out all of our kernel symbols. So essentially we need those symbols. Those symbols tell us where functions live in the kernel. Where do they live in memory? So we echo 0 to that to kind of disable it. And as you can see, the difference between grepping on that call sims before we did that, gives us all zeros, and then grepping on it after the fact, it gives us an actual kernel address. All right, so let's talk a little bit about the debugging workflow and the specific debugger that I'm using. So I am using GDB, but I'm not using the standard GDB. I am using GEF, which is the GDB enhanced features. As you can see, it provides extended features specifically for exploit development and reverse engineering. But I'm not using the standard GEF. I'm actually using this dude's fork of GEF that is amazingly actively maintained and really well maintained, actually, that provides a bunch of kernel-specific functions. So you could do things like kmalloc tracing. You could do the kernel symbol application, I'm going to call it. So essentially, being able to resolve those symbols within the debugger, which is possible manually, but this makes it really easy to do. You could do slub and slab inspection. So the slub and slab are those kernel level heap allocators that I mentioned before. So you could do direct inspection of those, which makes debugging very easy. And you could do things like page walking. It's got a ton of commands, definitely worth checking out. It also gives you nice syntax highlighting and looks a lot cooler than standard GDB. This was when I was going to do a demo. So just pretend I'm doing a demo. All right. Okay. So in my demo that didn't get to happen, essentially I just proved the concept of the POC. I ran it and we leaked memory, so we were able to achieve that out-of-bound read. We were able to read past that initial buffer object and read the object after it. So great. So now that we know that that works, we need a target. We need something to overwrite, right? So Linux kernel provides a number of targets that are useful for exploitation. A lot of commonalities between them are going to be things like containing function tables and function pointers, having fixed pointers that we could use for leaks, having some kind of read or write copy mechanism associated with it, and also having either a direct or indirect allocation from user space. We need some way of allocating that object where it needs to be. And this is kind of where another one of those hints that I mentioned earlier comes into play. In that initialization file, we saw some specific permissions set on these two files, and that we'll talk about what those files are in a second on our next slide, but that gives a huge hint about what we should be targeting here. All right, so what happens when you open that dev/ptmx is it actually allocates this tty struct object in the kernel, and you could see there the size of this struct is hex 2e0, which resides in that kmalloc 1k essentially cache, which again, that should be the same cache that we were targeting earlier with our proof of concept. So perfect. This is a great structure because we can get kernel leaks, we could get heap leaks through the various fields that are contained in this structure. It also has a magic field at the top, which is always set to the same value, which makes it really easy to identify in memory. So we know when we hit it and we don't. Bake that right into our exploit. And it's got this TTY operations function table, which we can use to redirect execution essentially here. All right, so let's think about our initial exploit strategy, knowing all this stuff. Again, I've labeled this as naive because there's some problems with it. So what we're going to do is allocate a buffer object in the same cache as that TTY struct, that kmalloc 1024 cache. Then we're going to allocate a TTY struct by opening the dev/ptmx. And then we are going to use our out-of-bound read to leak the TTY struct and validate that they are adjacent in memory. we're going to create a fake TTY operations function table, which we stick in the top of our buffer object there. And then we are going to try to write past and overwrite that TTY operations to point back to our function table. And then we're going to trigger one of the TTY operations, which should now trigger one of our functions and profit. But there's a problem with this. There's a lot of problems with this, actually. Well, actually, I'm sorry. Let me go back. So what are our problems? Well, how do we know where our function pointer is? How do we know where that heap memory is? We don't. So how do we know what to overwrite here? Well, we don't. And then what are we going to put in those function pointers? We don't know. So yeah, this is flawed. So some things that we need to do is, okay, to answer that first question, we need to leak pointers, right? So that out-of-bound read primitive that I talked about, we can leak that data, and that's exactly what we're seeing here. So I called out earlier that magic number. It is hex 5401. So when I see that in my leak, I go, great. I know I've leaked that TTY struct. I know it's adjacent. I also, sorry. I also get a few other things from this. So there are 3 types of leaks that are necessary to achieve our exploit here. So we need to leak the full TTY struct because when we're overwriting it, we don't want to clobber, we don't want to overwrite some of these necessary values, like that magic field. I believe also the TTY driver has to be pointing to a specific area of the kernel. So it's just a lot easier to leak it completely and then just replace the values that we want to overwrite and just kind of replay it essentially. Yeah, and TTY struct is a strong target because it provides all 3 of these leaks. All right, so let's talk a little bit about leaking the heap pointers. All right, so there is a specific command in gef, slubdump, which helps us to determine the heap location. So what I've got here at the top is you can see some of our leaks, and then you can see the output down here of that tool in gef. And it might be hard to read the addresses, but what we can see is within this cache, there's actually actively allocated the object that those leaks refer to. So there are 38 bytes and 48 bytes off from that object. So essentially, that'll show you that, hey, these fall somewhere within our TTY struct at those offsets. So yeah, there's also some other tools within gef, the kmalloc tracer. You can see when your allocations are happening, and you can see what processes they're associated with. It's really helpful for determining when you're allocating stuff and where it's getting placed and whatnot. All right, and now I'm going to talk about leaking the kernel pointers or kernel function pointers. So what we need to do is determine general memory area for kernel function pointers through that proc call sims. So what I mentioned earlier was we had to echo into that sys kpointer restrict to actually get these addresses. But now that we've got them, we can just read a bunch and say, okay, we've got an idea of where our kernel code exists in memory. Do any of the leaked pointers that we have match up or look like they live closely to that? And sure enough, we've got this leak at position 201, which looks awfully familiar to the leaked kernels pointers up there. We can also validate that. So what I did here on the right-hand side is I specifically grepped for that leaked address that I've got in the call sim, so in the kernel symbols, and I can see it's specifically associated not only with a kernel function, but with a TTY kernel function, so it's a pretty good validation there. So when we turned off KSLR earlier, it was to get these pointers. But once we have them leaked, we can actually just use that to calculate offsets to these different functions. So the KSLR will randomize where the base address is for kernel code, but all those offsets remain the same. So as long as we've got a stable kernel pointer leak, we can then just say, okay, well, I know, function X is, I don't know, 800 bytes away from it, so let me just take that leaked pointer, add 800 bytes to it, and I know that's where my function lives. That's the kind of thing we're working with here. All right. I'm going to talk a little bit about SMEP and SMAP. So supervisor mode execution protection and supervisor mode access protection. So prior to these mitigations, essentially we could have been game over at this point. We've have that ability to overwrite the operations functions and call our own code. We could just point back to user space where we've written some function that that gets executed, and voila, you've got code execution. The problem with this is what SMEP has done is it now prevents code from executing in user space when you're in the context of the kernel. And then what SMAP does, it prevents kernel context from reading and writing into user space. So this essentially mitigates that return to user style attack. All right, so how do we bypass this? So if you've done CTFs before, I'm sure you're familiar with return-oriented programming, or ROP. We're just going to do kernel ROP here. So kernel ROP is an exploitation method of redirecting execution by chaining together snippets of code, which we'll call gadgets, that exist within the program's memory to achieve desired functionality. So each ROP gadget ends in a return instruction. So I've got a little visual here, just kind of how ROP works in general. So really what you're doing is you're building a stack with these gadgets on it, and as each execute, they perform their little bit of code, and then they return back to this stack. So you can stack, so let's say, for example, we got gadget 1, and we've got some data above it. So we would expect gadget 1 to handle that data and then return back to gadget 2. Gadget 2 finishes, it returns back to gadget 3. Gadget 3 handles that data, returns back to gadget 4, so on and so forth. So you can really reuse all of the functionality within kernel code to achieve this. Also, it is kind of important to know how the return instruction works for this. So I've just got a little snippet on here. It pops an 8-byte value into the RIP register. That's our instruction pointer register. It is the next instruction that will be executed by your CPU. It then increments this RSP register, which is your stack pointer. So that keeps track of where your stack is by 8 bytes. And then it continues to the next instruction, which is in the instruction pointer. Unfortunately, I think I'm out of time. Yeah. No worries. Any time for questions or anything?
If they could do questions and meet you over to the side,
cool.
that'd be great.
Yeah, I'm sorry I didn't get to the rest of the talk, but if anyone wants to ask any questions, be glad to talk.